Last time we saw two more applications of Shira's lemma, one on counting independent sets in bipartite regular graphs, and the other one on counting matroids with the ground sets of elements fixed. Today we're gonna go back to graphs and see some more applications of entropy on some theorems that we're very familiar with. So let's start with one of the most basic theorem, the Mantel's theorem. Okay. So we're gonna prove Mantel's theorem, everything in terms of limits. So let's normalize everything and talk about density instead of the number of copies of edges or number of copies of triangles. So let's define for let's define this density. Let D in N, then we can define rho D to be the number of D clicks in the graph G. So more precisely, we should actually have rho D of G and normalized in a slightly stranger way. We're gonna to n to the d divide, we multiply the numerator by d factorial. Okay. If you recall, in Sidorenko's conjecture, we define this homomorphism density, TKD of G. This is precisely what's going on here. I just use a shorthand notation, rho D, instead of writing this long one, TKT of G. This is basically the proportion of maps from KD to G, which yields a homomorphism. But here, because KD, all the edges are pairwise, all the vertices are pairwise adjacent, such homomorphism necessarily is injective. So it actually yields a copy of the graph KD. Okay. And this is almost the same as what usually we call the KD density. Sometimes people also use number of D clicks in G normalized by n choose D this way, the unordered way of normalizing. When n is large, they are almost the same. So let me not distinguish these two versions. Okay. Now, so what is rho 2? Recall, rho 2 is the edge density of G, is T K2 of G, which is, in this language, 2 factorial, which is just 2 times the number of edges in G, normalized by n squared. Okay, this is the edge density. Or to be precise, edge density should be this one, but let me just assume these two are almost the same. So Mantel's theorem can be translated in terms of density is that for any triangle free graph, for any triangle free G, we have rho 2 of G is at most 1/2. Okay, so if you do the math, if this is at most 1/2, we get that E of G is at most n squared over 4. Okay, this is what we're gonna prove using entropy. Okay, so we're gonna start with something usual. We're gonna uniformly random sample an ordered edge, a labeled edge. Okay, so uniformly random. Ordered or labeled edge. Let me call it K2. And I will call it X1, X2. Now we're gonna do as we've seen in Sidorenko's conjecture, we sample XY, the labeled or ordered edge, uniformly from all ordered pair of edges. We're gonna do resampling. We're gonna resample X2, conditional on X1. So conditional on X1, we're gonna do another random variable, random sampling, so that the distribution of this guy is conditionally has the same distribution of X2. Okay, so let me first draw the picture. Blue stands for resampling. Now the second step, sample Y1, a random vertex Y1. Such that condition on, so here's Y1. Condition on X2, X1 and Y1 are identically distributed. Condition on X2, Y1 and X1 have the same distribution. And we do the same for the other one. We sample Y2 so that condition on X1, Y2 and X2 have the same distribution. Have the same distribution. Good. Now, we're gonna do something looks a little bit magic. We're gonna define another random vertex, but this random vertex has sort of two layers of randomness. So let's first sample a random variable R uniformly from the set consisting of elements 1 and 2. This is a very simple random variable. Then we define a random vertex Z. Let me call it U. Random vertex R to be yi if r equals to I. Okay, so here's the picture. We let r to be y2. If this little r, when we sample it, the outcome is 2. Okay? Looks a little bit strange at the moment why we do that. The thing is, we have all these random variable. Let's look at its join entropy. Now let's consider the join entropy. Let me maybe move this picture. Okay. Which joint entropy we're going to consider? We're going to consider joint entropy H of x1, x2, and this resampling, little r and capital R. Okay? Here's the picture again. So first of all, let's use, whenever we have a vector form, the first thing that comes into our mind should be a chain rule. So let's try to expand it. So by chain rule, we have the joint entropy, x1, x2, little r, capital R, equals to, let's first expose x1 and x2 and see what's the information we get out of this pair. And then, given that x1, x2 is exposed, let's see what additional information we get from little r, this simple uniform random variable, conditioning on x1, x2 are given. And at the end, we look at the last one, which is this random vertex having this weird 2 layers of randomness equals to y2 if little r equals to 2. So r given x1, x2, and little r. Well, this term, we know what it is. x1, x2 is a uniform random ordered pair of edges, right? So this is nothing but, by maximality, this is log base 2 of the space of x1, x2, which is 2 times the number of edges. So it's 2 times E of G. This we know what it is. This we also know. What is this guy? Well, R is actually independent of x1 and x2. Because how we define R? R, we just say that you uniformly at random choose it from between 1 and 2. It doesn't depend on x1, x2, the random ordered edge that we choose at the first place. So that means these two, it can be dropped by independence. This entropy is just entropy of a balanced by Bernoulli random variable uniformly distributed over a set of size 2. By normalization, entropy equals to 1. Independence and normalization, if you want, this equals to 1. So we have to estimate the last one. Let's see what the last one is. So the last one, let's write it down. This sort of double-layered random vertex, x1, x2, little r. Okay. Let's write it out using definition of conditional entropy. So let's recall the definition of conditional entropy on the side. Here's the definition. Is this color good? No. We have another color. So the conditional entropy, this guy, equals to the sum of all instances of x, the probability that x equals to little x, times the conditional entropy, well, actually of the entropy of this random variable. So if we think of this as a random variable, right? The marginal of y when x equal to little x, entropy of this guy. This is the definition. So now we're gonna let here, we're gonna expand it, let y to be this guy. Okay, and x is the r. So this equals to sum over all range of x. X is r here, right? So range of r is either 1 or 2. So equals to I into the probability that r equals to I times the entropy of y. Y is r conditioned on x1, x2, and then r equals to I. Okay. Good. Now here's the thing. Capital R and little r, they are related. If now we given that little r is I, we know that capital R is yi, right? This is how we define R. We're going to uniform we sample R between these two random variable, and the index agree with the value of R. So we can now rewrite this. And furthermore, this guy is 1/2 for each I. R is uniformly distributed. So now we can write it as sum I equals to 2, 1/2 times the entropy of yi conditioned on x1, x2. R equal to I, right? Okay, good. We can actually drop this now. Why we can drop this? Because yi is sampled. How we sample yi has nothing to do with little r. They are independent. So we can drop this guy. Okay. So this then we rewrite it as, and furthermore, as I said, let me write it. How we sample yi condition on the other x is independent of xi. So we can drop the one that has different index as this one. By independence, we have sum of, maybe it's not clear this way. Let me try. It's 1/2 h of y1, x1, x2 plus 1/2 h of y2, x1, x2. Okay. So as I said, by independence, conditioning on x2, y1, x1 are independent. So conditioning on x2, y1, x1 are independent. That means we can drop this guy. Okay. This is conditional independence. 1/2 h of y1 x2 plus 1/2 h of y2 x1. Well, these two are symmetric, so let's just write 1 equals to h of y2, let's say, x1. Now, let's write it in this way, because conditioning on x1, y2 and x2 are identically distributed, independently and identically distributed. So finally, we write this last conditional entropy in a very clean form. Any questions so far? Okay. Good. So let's summarize. We can rewrite the joint entropy as h of x1, x2, little r, capital R equals to this guy plus this guy, which is log 2e of g plus 1. Plus this last one, which we've simplified to this guy. So h of x2, x1. All right. Start with a new page and picking up from here. Okay. Now we're gonna bound this joint entropy in another way. Okay. So let us bound this joint entropy in a different way. So we use chain rule to expand it in a slightly different way. This time, the trick is that here's where we use triangle freeness in Mantel's theorem. Okay, how do we use it? Let's draw this picture again. How we use the triangle freeness is that, note, triangle free implies the support of y1 and y2 are disjoint. Okay. If there's a vertex that can both serve as y1 and also serve as y2, both are possible, you get a triangle, which is forbidden. So the choices for y1 is disjoint from the choices for y2. And how we're going to use that? Well, if we use chain rule to expand this in this way, equals to h of u, x1, x2, r plus h of little r, x1, x2, r. So basically, yeah, okay, let me first finish this proof. We write it like this, right? Now, look at the second term here. Okay. What I'm saying here is that little r is determined by these three random variables. So if we expose what x1 is, we expose what x2 is, and we expose what r is, we will know r is the neighbor of either one of these two. We will know which neighbor R is, either x1 or x2. If it's x1, we know that little r must be 1. If r in this exposure is the neighbor of x2, then we know, yeah. If it's neighbor of x2, then we know r equals to 1, right? So r is determined by x1, x2, r. Okay, maybe let me write down what I just said. After revealing x1, x2, r, we know r is in the neighborhood of x1 or r is in neighborhood of x2, right? In the former case, you have r equals to 2. In the latter case, you have r equal to 1. This is what I mean. And remember, one of these lemma that we proved called dependence. If one variable depends on the other, the entropy is 0. The conditional entropy is 0, which makes sense because this guy uniquely determined that we gain no new information from little r. So this equals to 0. If you want to summarize in words, this triangle freeness enable us to compress the entropy here to drop this little r. This guy is redundant. Enable us to compress the joint entropy. Okay. So we just need to bound this guy. Okay. To bound this guy, well, we're going to give an upper bound. To give an upper bound, because we want the upper bound on number of edges, what's the simplest way to give an upper bound? We know entropy of a random variable is at most log of its range. So we just need to estimate what's the range of this joint random variable. So let's look at all possible choices for x1, x2, and r. So here, the number of choices for x1, x2 is obviously 2 times number of edges. It's ordered or labeled edges. And the choices for r is obviously is at most n. Well, r is a random variable. There are random vertex. Number of vertices is n, so at most n. So the range, what that means is that the range of x1, x2, r is at most n times 2e of g. So by maximality, implies h x1, x2, r is at most log of n times 2e of g. So we managed to give a bound, double count this joint entropy. One way we get this. The other way, we compress little r, becomes this guy, and this guy we have upper bound here. Putting these two together and do the calculation. Okay, maybe let me change this one more time. This guy, by chain rule again, is h. Let me bound this guy. hx2 x1 by chain rule is hx1 x2 minus h of x1, right? And the first term is log 2e of g. This is uniformly over all ordered pair of edges. The second term by maximality is at most log n. x1 is a vertex, so you have at least this minus log n by maximality. So, putting things together, this is heart, you will get Mentel theorem. I will not do the calculation. Any questions? Okay, now let's see how we can strengthen our argument to obtain something slightly stronger. Well, let's recall some phenomenon called supersaturation. Mentel theorem saying that, so this is the same as E of G is at most n squared over 4. Mentel theorem is saying that taking the contrapositive, if E of G is more than n squared over 4, we will have a triangle. Supersaturation is saying if E of G is more than n squared over 4 plus a positive proportion of edges, not only will we see one single triangle, we will see a positive fraction of triangles, which is of order of magnitude n cubed. Now we're going to give a bound on the constants here in the front in supersaturation. This is so-called Goodman's bound. Okay. Theorem. So Goodman's bound is the following is the number of, for any graph G, the triangle density row 3 of G is at least 2 times, how do I want to write it? The edge density of G minus 1 times the edge density of G. Okay? This is Goodman's bound. So this function looks like 2x minus 1 times x. Let's first try to understand this function by plotting how it looks like. Okay, so this guy has root, this function has root 0 and 1/2. So at 0 equals to 0, 1/2 equals to 0. When x equal to 1, this equals to 1. So it looks something like this. The minimum points, 1/2 here. Okay. So let's read this graph. This is saying that when the edge density is less than half, so the number of edges is less than two-round graph on two complete bipartite, there's no guarantee of any triangle. Triangle density could be 0. Good. So it gives a lower bound on triangle density given the edge density. The first thing I should comment on is how good is Goodman's bound. So Goodman's bound remark is tight for all edge density of the form 1 minus 1 over k. Okay. So here, when k equals to 2, 1/2, the tightness is witnessed by complete bipartite graph. The next 1 minus 1 over k is 2/3. Let's draw what 2/3 is. And then 3/4 dot 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 dot. All these points of the form 1 minus 1 over k is tight. And the tightness, I will leave it for you to check, is what you might expect, the two-round graph, right? At 2 over 3, that's the edge density of balanced three-partite complete bipartite graph, complete tripartite graph. 3 over 4, it's four-partite. So on and so forth. Okay. Exercise for you to check. Just for the literature, it's tight at all these infinitely many number of points, 1 minus 1 over k, but at the other points, it's not tight. It's known that the best possible bound is piecewise concave that looks like this. This is the best possible bound. So optimal bound. Optimal lower curve is piecewise concave. Coming from this example, coming from interpolating these two examples. Okay, I will not say more on this. So let's try to prove Goodman's bound. I claim that to prove Goodman's bound, we can just modify what we've seen in this Mantel's proof. Okay. So how do we modify it? Well, first of all, let's recall Mantel theorem's proof. In the first way, we're going to do exactly the same. We will do x1, x2, random ordered pair of edges, and then do little r, binary Bernoulli, and then do capital R, which is a random variable taking value one of these two resample vertex, y1, y2, depending on the value of R. Exactly the same. We're going to analyze the joint entropy. In the first way, this chain rule, we break it down, we get exactly the same bound. Okay, so let me write down this bound. Continue as before. Let me write down this bound. Proof of Goodman's bound. Proceed as in Mantel's theorem. That means we're going to sample x1, x2, little r, capital R, blah, 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 and we get this thing. We get that H, the joint entropy, is at least, let's put these two together. So 2 of log of this guy plus 1 minus log n. Okay. So we have one bound here. Now let's estimate in another way. This is where it differs. When we estimate in another way, again, we're gonna break up this joint entropy. Yeah, okay, so Changfang is asking why we need to specify this random variable little r. That's a good question. Maybe we can just define R to be uniformly distributed over these two, right? We can define this way without specifying little r. I think there is a way to write things without little r, but with little r's, it will be much easier to present it, to argue. Okay. And with this little r, we can sort of, this little r, we sort of see where this redundant information coming from, where we exactly use. Sort of. Without little r, it's some of the identity when you try to argue it, it takes extra effort. Okay, so now we're gonna bound it in another way, which is here, written here. We break up the chain rule in this way, destroying entropy. Now, the second one is not zero anymore. In Mantel's theorem, using the triangle freeness, we know that little r is completely determined by the other three random variable. But in Goodman's bound, we could have triangles. So y1 and y2, their supports are not disjoint anymore. This is not zero anymore. So although this bound is still correct, this bound is still correct. So we need to redo this part. Let's try to do that. So let's again, we want to bound. Now we bound h of x1, x2, little r, capital R, from above as follows. So again, all we're going to use is maximality. We're going to analyze how large is the range. So by maximality, this is essentially the only way how we can bound entropy, basically. H of x1, x2, r is at most log of the range of this guy, right? So let's analyze what's the range of this quadruple. What are the number of choices for them? Okay. We have to distinguish two cases now. So let's draw this picture. We have x1, x2, and we have r. So remember the original picture that looks like this. You have y2, y1, and r is one of it, depending on what the value of little r is. So now, in case 1, is when x1, x2, and r, when you review it, the choice, they form a triangle. This is case 1. We could have triangle now, so in this case, let me draw the picture here. When they form a triangle, this means I review the value of x1. I review the value of x2. I review the value of r. Now they form a triangle. If this is the case, we don't know if r is the resample of x2 or r is the resample of x1, conditional x2, because this r could be both y1 or y2. Okay? So in this case, the choice of r is is 2. And the choice of x1 and what should I say? The choice of little r, sorry. The choice of little r. Okay. So when these 3 vertices from the triangle, then the choices for little r is 2. Does it make sense? Once again, if they form a triangle, then capital R could be either one of these. We don't know. So little r could be either 1 or 2. Okay? So that means the total number of choice is at most, well, when they form a triangle, so this is ordered triangle, so this is 3 factorial times the number of triangles. And let me let t to be the number of triangles. Okay. Times 2. Okay. The second case, when x1, x2, r do not form a triangle. This is similar as in Mantel's theorem. So you have x1, x2, and r, we review r, and notice that r is a neighbor of x1. In this case, we know that little r must be 2. The choice of little r is unique. Then there is only one choice for little r. In other words, r is determined, as in Mantel's theorem, by x1, x2, and r. This instance of x1, x2, and r. So here, the number of choices of x1, x2, r that do not form a triangle. This implies total number of choices is at most. Well, we have, what's the total number of choices of x1, x2, and r? Well, x1, x2 has is ordered pair of edges. So this is the choices of x1, x2, 2 times number of edges. The number of choices for capital R, it's a vertex, so it has at most n choices. Among all these choices, we have to deduct those when they form an ordered triangle. That has been counted in the first case. So that's minus 3 factorial times the number of triangles, which is t. And for all this is the upper bound on the number of choices of x1, x2, and r that do not form a triangle. For such choice, there's only one choice for r, so multiply by 1. Okay. Put these two together, we have the range. This implies the total number of choices for x1, x2, little r, capital R is at most. If you sum these two up, we get n times 2e of g minus 3 factorial times number of triangles, but plus 2 of that. So just plus 1 portion plus 2 times, there's no 2, plus 3 factorial times t, number of triangles. Okay, that's it. So we have the joint entropy is at most log of this guy. T. Okay, t is the number of triangles. Now let's do the calculation together to do the sanity check that we do have this 2x minus 1 times x function. All right. So we have on one hand, the joint entropy is at least this guy. On the other hand, the joint entropy is at most this guy. Putting these two together, so the top one, 2 times log this, blah, blah. We have thus, how does it look like? 2 log 2e of g plus 1 minus log n. Oh, I can do this. Perfect. Copy. Well, actually, why don't I just copy everything? So I just want this piece here. Okay. Okay, give me a second. Let me erase these. Okay, finally. This is at least this guy. Now let's do the calculation. So let's merge the log on this side. This equals to log How do I do this? Let's do log. I move 2 inside, becomes square. So 4 times E of G squared. Let me just write E of G squared plus 1. So I need to multiply by 2 again. So it becomes 8 minus log n. So I need to divide by n. Okay, that's the other side. Is that correct? Log 2 seems correct. So this implies n times 2e of g plus 6t is at least 8e of g squared over n. And what's our goal? Row 3 is at least 2 row 2 minus 1 times row 2. Okay, and recall, row 3 is what? Is the number of triangles times 3 factorial over n cubed. And this row 2 is 2e of g over n squared. Okay, probably right. So 6, this implies 6t is at least divided by n cubed, write it as row 3, is at least 8e of g squared over n minus n times 2e of g divided by n cubed equals to 8e of g squared over n to the 4 minus 2e of g over n squared. Now this is exactly row 2. And this is hopefully 2 row 2 square. Is that right? 2 row 2 square is yes. All right. We do calculation once. That finishes the proof. Any question? Okay. So this is Goodman's theorem. Originally, I planned to present an even more general case, but I think I'm running out of time. I want to move on to the next topic. So let me just state it, and then I'll leave it for you as exercise to prove an even more general version. You can extend this proof to obtain relations between clique densities, not only in row 3 and row 2, triangle density and K3 and K2 density. You can get relation between KD plus 1 and KD density as follows. So exercise, extend the above argument to prove the following. Okay. Theorem. The clique density for D plus 1, the ratio to row D is at least clique density of D, the next pair, row D minus 1 times D over D minus 1 minus 1 over D minus 1. Okay? This is the exercise. From here, you can derive, if you let D equal to 2, that's Goodman's bound, right? Remark, E equals to 2, you can check this, what we just proved, Goodman's bound. So that's a corollary. Another corollary is that we can have, you can do calculation to show that you can do calculation to show that rho d is at least product of I equals to 1 to d minus 1, 1 minus I, 1 minus rho 2. Okay? Another corollary is we prove Mantel theorem, right? This theorem is enough to derive Turan's theorem. So all these I will leave as exercise. Exercise, exercise, exercise. Simple ones. Any question? Okay, if no, let's move on to the next topic. I want to talk about another very cute applications of entropy, Schur's lemma. But let me state a very special case of Schur's lemma. So a special case of Schur's lemma. This is application is Hopper's edge isoperimetric inequality. Okay, to state this theorem, let me first say the tool we're going to use. It's called a Hans inequality, a special case of Schur's lemma. So Hans inequality says we have x1 to xn, discrete random variable. Then we have their joint entropy is at most 1 over n minus 1. The summation of I goes from 1 to n. The joint entropy, but with I removed. Okay. So this is Schur because in Schur's lemma, our coordinate is 1 to n. Each coordinate, when you range over different I, appears in exactly n minus 1 of them. So this is a very special case of Schur's lemma. All right. We're going to use this special case to prove Hopper's edge isoperimetric inequality. So let's state this theorem, a very fundamental result. So hypercube, so we know what is hypercube. Let's see how I want to state it. I want to use, right. So hypercube, let's recall, is a graph where the vertex set is just binary vectors of length n, and you have an edge if and only if their Hamming distance is 1. The number of coordinates they differ is 1. If and only if Hamming distance, which is the number of coordinates they differ, equals to 1. So here's an example for hypercube 3-dimensional, just nothing but 3-dimensional cube. Okay, so each vertex you can think of as a vector. This is 0, 0, 0. This is 1, 0, 0. This direction, let's say 0, 1, 0. This is 1, 1, 0, 1, 1, 1. What is this? 1, 0, 1, I guess. This is 0, 0, 1. This is 0, 1, 1. Okay. Now, edge isoperimetric inequality is saying if we given a subset of vertices of hypercube, how many edges going across this set to the other side? But we're gonna phrase it for convenience. We're gonna phrase it as how many edges stays inside this set A because this graph is regular, so it's the same. So this inequality is saying given a subset of vertices of hypercube, how many edges in this hypercube? So the Harper's edge isoperimetric inequality basically says that for any subset of vertices A of the hypercube, let's say Qn, n-dimensional hypercube, the induced subgraph Qn induced on A has average degree and most log of A. Okay, so let me state this theorem. Exactly what I just said. For any A, let me state it in a slightly different way. Then the number of edges in A, this, what I really just mean is the induced subgraph on A, all right, is at most 1/2 A times log base 2 of A. Okay, so the average degree is 2 times the number of edges divided by the number of vertices. So this is the average degree. This bound is optimal. So the maximizer is lower dimensional subcube. Let's see. Remark. This bound is optimal if A induces, let's say, d-dimensional subcube. Okay, then QNA is, what it means is that QNA is QD. Then what's this? This graph is D regular, right? And what's the size of A here? Size of A is 2 to the D. Log 2, log A is D. Okay. Any questions about the statement? Good. We're gonna prove this theorem. So let me introduce some notation. The first notation is the number of edges in the hypercube, we can sort of give it a direction. So this is, vertices are n-dimension binary vectors. So n is the coordinates. We have n directions. This is direction 1, first coordinate. This is direction 2, second coordinate. Up is direction 3, the third coordinate. We can naturally partition the edges in the hypercube according to direction. So I will write, we can also partition edges in A in terms of its direction, which way it's facing. So I will write E sub I of A to be the direction I edges in A. So let me write EI of A, the number of I's direction edges in A. Okay. So for example, if this is our A, This is our A. Then the third direction A edges is these two edges. Maybe I will draw this picture. Give me a second. So this is A. Well, let's make it simple, just like this. Then this one is E3 of A, right? And this one is E2 of A. And this one is E1 of A. Okay, good. So in this way, EA is nothing but sum over all directions EI of A. The idea of this entropy proof, let me first state the idea, is to relate the ith direction edges in A with, so the idea, first thing is we have already a set of vertices in A. So one natural thing to do is to sample a random vertex inside this set. Okay, seems natural. Then log A is basically the entropy of X. Let's do that. So uniformly sample a random vertex X inside the set A. Then we have, the good thing about this is that the entropy of X now is log of cardinality of A. So what's in the statement, it can already be expressed as entropy. Now the key idea is that X, you can view it as x1, x2, xn, right? After all, X as a vertex in in A and also in hypercube is a length n binary vector. So each xi takes value 0 or 1. The key idea is to relate the ith direction edges in A with the conditional entropy h of xi, the ith coordinate of this random vertex I, and the remaining coordinates. Does this look familiar? This guy is exactly the thing in Hans inequality here. Okay. We will see how we can relate ith direction edges to this conditional entropy. But first, let me make the notation slightly easier. Let me write as shorthand xic to indicate the vector with xi removed, omitted. In this notation, then we can rewrite this as entropy, conditional entropy of the ith coordinates and the remaining coordinate, the complementary coordinates. Okay. All right. Proof. Well, we have our random vertex, a random vector, uniformly sample in A. So we can expand using chain rule this random vector. So by chain rule, let's do that. We have the conditional entropy of xi plus equals to, right, equals to the entropy of the whole vector minus the entropy of the vector with xi removed. This is just chain rule. Okay. Remember, the union of everything by xi and xi is x. Okay. Good. Now let's use the definition of let's first do the easy thing. For this, we sum over all I. What do we get? The summation of I from 1 to n, hxi, xic, this conditional entropy, which will relate to the i's direction edges, but that's for later, is the sum of, this is what we get from chain rule. Move this here, hx minus hic, I from 1 to n. And here is where we use Hans inequality. By Hans inequality, you can check this is at most the entropy of x. Simple application of Hans inequality. But we know what's entropy of x is log of a. Okay? So our claim now is to prove, it suffices to prove the following claim. The claim is, with the idea here, this conditional entropy, we can express it as the i's direction edges. H, xi, xic equals to the i's direction edges in A times 2 over size of A. If this is true, let me first derive the final result. If this is true, this will imply the left-hand side here equals to sum over I EIA times 2 over A. But this is E of A. So equals to 2 over A E of A, which is at most right-hand side, log A. So the size of E of A is at most A over 2 times log A, which is exactly what we want to prove. A over 2 times log A. So it suffices to prove now this claim. Any questions so far? Okay. Let's prove this claim. So how do we prove this? Well, we need to draw some pictures. First, let's use a definition of conditional entropy to write the left-hand side. Proof. By definition, xic equals to sum over all possible choices for, for vector, if you have a vector length n, I will write xi for its, we usually write x1 for its i's coordinate, right? Now I will write xic for the vector with same, with i's coordinate removed. Okay, so for every choices realization, choices for xic, you look at the probability that capital Xic let me write P X I see. This is just shorthand for the probability that all the other coordinate takes value this guy, okay? Times the entropy of the i's coordinate given that the remaining coordinate looks like this. Any questions so far? Just the definition, okay, of conditional entropy. Just the definition. Now let's first look at this conditional entropy. Now, for this guy, h of xi, xic equals to little xic. It's good now to draw a picture. To illustrate, let's take okay, and let's say our A is this guy, this guy, this guy, this guy, and this guy. Why not? So this is our A. And let's say this direction is the i's direction, the vertical direction. Now, okay, each one of this horizontal plane, this hyperplane, codimensional one cube, is the range for all possible choices of these other coordinates, right? Okay. The key point here to associate to the number of edges in A is that in the i's direction, if the choices of, let's do two cases. If for xic, if this xic do not support an edge of A, meaning that the other side in the i's direction is not in A, then upon revealing that the other choices is this guy, we know that the i's direction of the i's coordinate of xi, there's only one choice. It can only be here because the other side there's no choice, right? So let me write it down. If xi does not support an edge, or by support does not is not incident with an ith direction edge, in A, then if you reveal that xic is this choice, I know that the i's coordinate has to be at the bottom level. This is 0. This is 1, right? I know xi has to be 0. There's only one choice. So this is deterministic. There's no surprise, no information. That means the conditional entropy equals to 0. In this case, this is 0. In the second case, if xic is incident to a i's direction edge in A, so for example, if xic is this guy, then because x is uniformly chosen in A, now I'm saying when we uniformly chosen a vertex in A, what's condition on the choice of the other coordinates, these two vertices are equally likely to be picked in A. Okay, that means xi condition on this is uniformly distributed over an element, a set of size 2. Then xi is uniformly distributed over these two. Okay, meaning that this entropy, conditional entropy, is 1 by normalization. Okay, so now we can write this guy. Since if it's not incident to an edge, this entropy is 0, we don't need to care about those. So we only need to care about those probability when xic is incident with an supporting an ice direction edge. Okay. Actually, this is not a xic is not a vertex. It's a projection of a vertex. So supporting is more appropriate, I think. It's not supporting an ice direction edge. Okay. Is supporting. This is more appropriate. Later in the notes, I will make this more rigorous. Right. So that means the conditional entropy we want to bound H xi xic equals to sum of xic supporting an ice direction edge in A. Pxic times 1. In this case, this conditional entropy equals to 1. Now we are almost done. Why? First of all, notice that the number of summon, the number of the projection, the choices of xic where it supports an edge is precisely the number of edges in the ice direction in A. This is precisely EI of A. So we just need to look at this guy. What's this guy? Well, if we already know that this choice of projection, if already know this choice of projection supports an edge, okay, so we fix all other coordinates already. That means we have x is chosen in here. So this means condition on xic uniformly distributed here. Condition on xic equal to little xic, where it supports an edge, right? So that means the probability of this is 2 times the probability of 2 vertices in A, which is 2p little x for x in A, which is 2 over A. Once again, what do I mean here? This might be a little bit fast. If we already know this projection supports an edge, then the marginal probability of this projection, because x is uniformly sampled in A, every vertex, every this red dot has probability 1 over A, right? But I know for this red dot, its twin is also here. And choosing any one of this red dot will realize this good projection, which supports this particular edge in ice direction. So both of these choice is good. That's why it's 2 over A. Any question? Then this is it. That we are done. So equals to EI of A times 2 of A. That's precisely the lemma. Any question? Okay, if there's no question, we're gonna continue next week. Thanks for listening.